Okay, so let's go over this one. So in the first, let's see, it's made of this. Okay, so this reacts with ammonia, and the product of this reaction is, who would like to draw that on the chalkboard? Samson.
Oh, go for it.
Yep, so that forms a, is there a carbon nitrogen double bond there?
Yeah.
Yeah. Okay, so that forms, what's the name of that group?
And amines.
Yep, that's an amine. Okay, so then that reacts with NaCN and H2O, and what happens next? Okay, so this is the same thing you did before. So that imine, which atoms in the imine can a reaction occur?
Carbon.
Anywhere else? Okay, so treat that imine the same as a carbonyl.
So the CN attaches onto it.
CN attaches to the
Carbon.
and
Is there a name
forms.
for that, or is it just an amine carbon? Amine carbon.
Yeah, whatever it's called.
And so that forms a nitrile, and you can use H3O plus to turn the nitrile into acid.
Okay, so who would like to draw the next product? Okay, so now we treat this compound with NaCN, Because like I said, note that, don't worry about the Na, so that's Cn minus. So you said that the Cn is going to react where? Yeah, so it'll react here. And what kind of reaction do you think that is? Acid base, substitution, elimination, or addition? Yes, an addition reaction. So the product of that reaction is going to, who wants to write that on chalkboard?
What is the ended hydrogen? H2O.
Yeah, so what do you think of Jackie's structure?
Both of those need an extra hydrogen.
Yeah, so you need an extra hydrogen where?
On the EV and the
Yes, you need one here, because there's only two bonds to this H, so we put another one there. And we need to put, let's see what the other is. And we can put another one here.
Yeah.
Okay, so, okay, so that's compound B, and then that's treated with H3O plus, and that's, when we treat with H3O plus, what happens?
natural carboxylic.
Yep, so the nitrile is converted to carboxylic acid. So, Roberta, you want to draw the structure of alien on the chalkboard then? Okay, because in that nucleophilic addition, there's a proton transfer, so you can either come from water or
It really is. It would always be even.
yeah, so that's
Is any other specific condition like
the hydrochloric acid. Okay, so based on that, can we go back and do this one? Or should we just keep on going? Listen, we have one more, we have this one, we have at least two more slides. And it's almost 5.
Let's just try to do that one.
Okay, so can you use those things we did there? Because no, what happens, you use the Cn minus to form a carbon-carbon bond there.
So are you saying that we should add on an aldehyde to our phenol group?
Yeah, so exactly. Yeah, so if you wanted to make this compound, where would we put the phenol group here? So where's the phenol group go?
The R.
So are you saying that the phenol group goes here?
Yeah.
So make this pH for phenol.
Yeah.
So you want to try that? So can you make this compound? In other words, can you add this to the phenol?
And then just get rid of that methyl.
Yeah.
And then you just do the same thing.
Yeah, so if you do that, yeah, so can you do that? That's the only thing, you need to figure out the substitute. Remove part of the matrix.
This one's not doing it. We found a way to actually make that whole now we just gotta add on this and add both of these here. This how to take the right side. This how to which one you house is like the other one what's your hand offers the other see there's like a major like wedge in there's something like that. And you actually use this as this more. But it's
I looked it up. There's no science and one oxygen that's this is just
is there a way to reduce this?
Either stronger, reducing it, then it goes all the way down.
It's for days long with them.
Actually, that is strong reducing.
You were saying, I didn't feel it about.
Okay. You just made this whole thing about you. You want to see this, can you repeat that?
Can HCl reduce the acid? Fe and HCl reduce acid, like the acid. Will it reduce the aldehyde as well? Will it reduce the
Actually, I know you're so mean, like
Because I'm kind of head on. I don't know which one to add first because in order to have it as long as reducing agent, and aldehyde gives an oxide agent. So I was just wondering if I use this, the presence of acid. So if I use that, this would be present, right? Okay, so Fe as well. So this will use Fe. It is after this.
Did you say you were going to have
I'll do it.
Ashley, what did you put in here? It's like, it's different. It's good, but there's something, I kind of heard that.
Magical.
That's what it is. It's my mom's recipe. I don't know. I think it's standard. Is it? No, I had one this morning,
Around 11:30 in the morning.
and then this one, it was like, it's good, it's something different. But I can't put my finger on it. But there's a taste, it's very familiar. It's a good routine. I had the cookies yesterday.
Are we done?
They were not good. Why? There's no butter or nothing. And you don't pour eggs. It's just like applesauce substitute applesauce for all those ingredients. And this one? Not this one. Oh, no, the vegan ones from yesterday. And then you, I guess you put some special kind of chocolate chip in it. And it's
Are we gonna do any more?
Yeah, a couple more slides.
I really like
Whatever you want.
anyway.
Can we move on to the next one?
Okay, did you guys figure it out?
Yeah.
Okay, so how you guys gonna do it?
Same way we just did it with this one?
Okay, let's keep on going then. So, look at this one.
Now, everyone's trying to figure out.
Where will the reaction occur? Here's another amino acid. So where will the reaction occur with this one? Yep, at the acid. Yeah, so you know it's going to occur at the acid or at the carbonyl carbon. How would it at the nitrogen? Here's the alpha. Here's an alpha carbon. Can something happen there? Yeah, we talked for about 2 minutes on that alpha halidination. I'm not going to ask you that.
Are we going to do like birch?
Nope. But what about this part here?
Is it aromatic?
Yeah, that's a good question. Is it aromatic?
Yes.
How do you know it's aromatic?
Yes, I But I
Yeah, so
didn't
it's
have
there,
one
man.
here.
Lone pair on the nitrogen. So first is it conjugated?
Yes.
And what were the other criteria for a compound to be aromatic? It says it's conjugated, it's got to be a ring, it's got to be all the odd electrons have to be on the same place. You got rings got to be planar. And the Huckel rule, the 4n+2 rule. So let's see, it's either has to be 2 or 6 or 10 or 14 pi electrons. So it doesn't fit. How many pi electrons are in this ring or these 2 rings? Yes, we have 2, 4, 6, yes, we have 10. So we include the lone pair on the nitrogen, we had 10. So for an aromatic substitution reaction, where would it happen in the ring or those 2 interlocking rings? Okay, so Noah, how would you figure that out? How would you figure out where an electrophile reacts? In other words, at which pi bond would you see a reaction occur?
Is it actually more than a pylon or no?
Well, see, if it was a lone pair by itself, the answer is yes. But then if it's part of the pi system, the answer is no. They're all equal.
Would it be the one that's less sturdy?
Could be, but how would you figure that out? Okay, so remember when we looked at benzene,
The one that's more stable.
yeah, so we looked at benzene, what do? We said that benzene, the pi bond behaves like a nucleophile that reacts with the electrophile, then we can figure out the intermediate that forms. So let's see, we put the electrophile here, where's we're missing something from this. On which carbon? Yeah, this one. Okay. Or, if we put a substituent on the ring, say let's put some R group here. We'll do the same thing. But remember in class, what do we do to figure out where reactant we have to? So in other words, we have to figure out, so you can either react with this pi bond or that one or the other one. So if you look at this one, how would you figure out which pi bond it reacts with?
The one that's more sturdy.
The one that would give a tertiary carbocation.
Yeah, so you want to try out and test out the possible ones and figure out which one's more stable. Because although it could be tertiary carbocation, note that when we looked at this one here, can you draw resonance structures?
Oh, wait, you can.
Yes.
Yes, you could, because for example, using a curved arrow, you can go from here to there, and those are one resonance structure, and so on. So you have to draw resonance structures for this one. So for example, you can say, when we start from this one here, let's just do one.
So which one would be like the more?
Okay, so let's just answer your question, I think. Let's do this. Let's see, then. Okay, then we have the rest of our molecule here. Okay, so choose one. So for example, let's say we have our electrophile, and just choose one pi bond. Okay, so let's say that maybe it's this one. Then if you don't like that one, then try another one. Maybe try this one. And then see if you can draw resonance structures. Well, if you don't like that one, then you can do the other one too. You can do this one. Or you can do that one. Okay, so that's where you can figure out where on the ring it's gonna react. Because really, you know, there's a lot of compounds which contain benzene, but then since a lot of you are studying biology, you know, this is one of those amino acids. So they have what's this ring called? Is it I don't know, pyrrole ring or pyrimidine ring or I don't know what it's called. I have to look it up. Right there.
So which would we look at?
Oh, yeah. So you want to try each possibility, and then you draw the resonance structures, and then figure out, okay, so which one do we get? Like a tertiary carbocation on one? That would give you an idea if that's a stable one or not stable.
Well, what if one had more resonance structures but wasn't on the tertiary?
Well, the priority is, although there's more resonance structures, you still want to look at the tertiary.
So looking for resonance structures makes more sense
tertiary?
Because it could be more than one. More than one pi bond could form a tertiary carbocation intermediate.
So just by looking at it and seeing that part of the pi bond connects with the tertiary carbon, we can't just.
No, you can, well, yeah, you can try that, do that, but then try some of the other ones too, because when you draw the resonance, remember when we were doing these? When you do the resonance structures, for example, this should be the orthopara. In our group, is an orthopara, that's what we'd be doing it. You could do it from, say, this pi bond or that pi bond, where you would get the stable tertiary carbocation intermediate base for molecules. Is there another way to do it? Yeah, that will work.
Oh, that's an alcohol. Yeah,
because note here that we want to put this methyl group on which carbon? That's the alpha carbon. So whenever you see that alpha carbon, we know that we can do what with that alpha carbon?
Acidic protein.
Yeah, so there's that acidic proton. We can remove that acidic proton with the base, strong base. And then we have a lone pair here, and then that forms that's a nucleophile, and that can react with,
Carbon.
yes, that's one way to do it. So, okay, so then let's just talk briefly about another way we can do it, or at least another possible way, and that was that because we said that using this method, okay, so what will we use here in this step? It's not working. Yeah, what will we use here? Joseph? See, you guys sound like organic chemists using all those abbreviations, LAH and MEI and OET. See, for me, I try to avoid using those abbreviations because I don't want to think of myself as an organic chemist. I'm the inorganic chemist trying to keep the chemistry warm. So is there another way to do it? So note that we're alkylating okay, so we're alkylating the alpha carbon, but is there another way to do it? Because when we talked about this in class, according to the text, they said that this is actually not the best way to do it because the yields are poor. And the yields are poor because actually if you use MEI, that'd be fine. But if you use the bigger alpha halide, not only do we get the substitution, we also get the elimination. So that's not why often the yields are poor. So there's another way to do it. What's the other way to do it? Or the other possible way to do it? Yes, the other possible way to do it would be to use the, we talked about this briefly, either that malonic ester or the acetic ester synthesis. Because see, in this case here, we get one of these. For example, I can't remember which one of these. So this one, or it's this one. Remember that? Then from there, you can do the same thing. So we'll treat each of these with a base, form this.